So hello everyone, in this lecture I will briefly discuss some of the state-of-the-art approaches we see these days in machine learning. So this is mainly driven by a field called deep learning, which uses neural networks to feed very complex neural network architectures to large amounts of data. And so I will discuss some of these architectures and also show you how they are very relevant in biomedical research these days. This includes automatic diagnosis from medical images, as well as folding proteins from their primary sequence structure. So neural networks, so this is the basic component of deep learning these days. Neural networks are actually kind of a more complicated logistic regression. So they are logistic regression classifiers, but they are put in some sort of an architecture and a hierarchy, and I will explain that in this slide. And so we've seen logistic regression. We had this model here, so we had this linear model with our logistic function here, this sigmoid function. Okay, we had our model parameters, which we try to optimize based on our loss function, right? Okay, so at m features here. And so if you look at the very first paper, so we're talking 1957, very first paper by Franklin Rosenblatt. This is the image that appeared in that paper. So this is what they call the perceptron, so the first architecture for a neural network. And you can see that it looks very much like this logistic regression here. So basically what we have is we have our features here. So in this case we had P features, and they were referred to as capital A. We use small x for that. And they also have weights. So in neural networks, people typically use W's. We will continue using these thetas here. So the thetas correspond to the W's. And then we have here our model. So here this would be the linear model. So this would be this summation here. Okay, and then we have our threshold, which should be a non-linear function, and in our case we had this logistic function here, so that's what the threshold is doing here. I can show you that here as well. So that's this threshold that we have, and that is also that was also the case for this logistic regression that we saw in the previous lectures. So now I can, as such, I can write this logistic regression like this. So what we have is, in this case, we have like three features. So x1, x2, x3, and we have additional feature for the intercept, which is always has a value always equal to 1. Okay, and then we have our thetas, which we will represent by these connections here. So each of these connections here has a certain weight, right? A certain model parameter, which are our thetas. Okay, so these are the things we want to learn from the data. And then we have this, what we call the activation node here. So I will explain the superscript later, but we have this activation node. And so what it's doing is actually computing the model. So this is summing, making this linear combination of the weights and the feature values, and also applying this nonlinear function, g, in our case the sigmoid function, right? And that will give you a prediction. Okay. Right, and we will explain later why we use this capital theta for this. So now what I can do is I can add another logistic regression model. So you can see here in blue, this was our previous model, right? So now I have another one in green, right? Okay, so we have a different activation node here, which will be the weighted linear combination obtained from the green connections, right? So here it was from the blue connections, so the green will have different weights compared to the blue, okay? And so that would give us this particular activation here. And so then on top of that, we can put yet another logistic regression, okay? And so the features for this logistic regression is going to be the outputs of these logistic regressions that we have here. Right, so we have two logistic regression, how shall I put this, architectures, okay, and we combine them in this more complex architecture by saying, okay, I'm going to take the output of this blue logistic regression and the output of this green logistic regression as the input for the next logistic regression, and so we also need an intercept here, right, and so we can do that again. So now we have yet another logistic regression, right? And so we have a different activation here. We can use that again as the input to our higher level, next level logistic regression, which will also be learned from the data and which will take as input the outputs of the previous logistic regressions. Okay, and so since here we have this non-linear transformation each time, the whole thing becomes a complex non-linear model. And we can write that model like this. So this will be the formulation of what we see here. Okay, so just very briefly, we have our first activation here. So this would be this one, right? Okay, so that corresponds to the blue logistic regression architecture here. Okay, so that would indeed take all for each of my features. We would have these model parameters here. So this would be the blue connections. Okay, and the idea in the activation node here is to take the weighted linear combination and then put it through this nonlinear transformation, which was the logistic regression function. Yes, so that's for the blue. We also have the A2, which is this one, which corresponds to the green, right? So we compute that like this, and keep in mind we have different model parameters for each of these, and the same is for A3. Okay, we get this, and then eventually we get to the higher level logistic regression here, which takes as input the outputs of the previous logistic regressions. So that would be the A1s, the A2s, and the A3s, right? So these ones plus our A0, which would always be 1, but that would be assigned a weight, so we can have an intercept. So that's what's happening here. And so that would be our final model, which is what I'm showing here. So even though this formula looks relatively complicated, once we look at it like this, it's actually very straightforward, right? And so again, just like with logistic regression, we will use some sort of gradient descent to fit all of these model parameters to the data in order to minimize a loss function. So this loss function can look something like this, right? So we can see this looks rather complicated. We have our model parameters, capital theta here, which we want to optimize, and we do that by minimizing, I'm sorry, here this should also be capital theta. We do this by minimizing this loss function here. And if you look very carefully, you can see that this is very much the same as the loss function used for logistic regression, right? So we have these two terms here. So this term would contribute to the cost function in case our label is 1, and this term would contribute in case our label is 0. And we can see you can see here how much it will be contributing. And of course, we have seen in logistic regression that if the error that our model makes is large, then the contribution will be large, and if the error is low, the contribution will be low, right? The only difference is, of course, we have a lot more sums here because we have to run over the different what we call layers in the neural network, right? And so again, here we also can have a regularization term here, which tries to keep all of the values for these model parameters as low as possible, again, of course, controlled by a regularization hyperparameter. So the way this is trained, so the way these model parameters are fitted to the data is very similar to the gradient descent approach from logistic regression, except in this case slightly more complicated, and the approach is called a backpropagation. So training neural network is typically done by a learning algorithm called backpropagation, but it's very similar. It's also it takes steps towards a smaller value for the cost function. Okay, so it iteratively changes the model parameters by looking at the errors that are being made and making sure that in the next step the model parameters are adjusted in such a way that you will perform better in the next case. Okay, so up to now, so these activation functions that we use are very important. So they make the model non-linear, so it allows the model to compute non-linear relationships. And so up to now we have used this sigmoid activation function, for nonlinear transformations, but others exist as well. So one other one very popular is the Tanyes, and typically these days people use these piecewise linear functions, in this case the ReLU, which is very simply the max between 0 and the value itself, so this would be a linear increase, and these show really very promising results, also because of course they are very simple. And since we're dealing with these huge neural networks, so they can have like hundreds of thousands to millions of model parameters in them, and so computationally that becomes quite heavy as well, and so ReLU is one way to keep that under control. So if we compare the architecture or the model of a neural network, which can become quite complicated, we can have different layers of logistic regression algorithms, and in each layer we can have different number of nodes, different number of activation nodes. So if you compare that, at least these guys did that, if you compare that to a decision tree, as you're showing here, okay, so then what they found is that if you would take a decision tree, you can model any decision tree with a neural network with 2 layers, right? And so what they show is that if you make the decision tree more complex, right, by having these different depths here, so you can have very complex decision tree, then that doesn't mean that you need more layers in the neural networks to be able to model the same thing as this decision tree can do. No, you just need more nodes in each layer, so more nodes in the layer, okay? And so with 2 layers, you can model anything that any decision tree can model. Also means that if you have more than 2 layers here, 3, 4, 5, 6, okay, you can model much more than the decision tree can do. So that's why these architectures, these models are much more powerful than decision trees. And so what happened the last decade, let's say, is that while we were using these traditional machine learning algorithms, so neural networks existed already back then, but people didn't really know how to train them well. I mean, they had this huge amount of model parameters. It was computationally quite expensive to train them all, and it was very hard to not overfit the data. And so last decade people found really good ways of preventing this overfitting, having different types of regularization, and that actually combined with, of course, much more data that we see these days, and combined with much more computational power. So this is basically driven by graphical processing units, so graphic cards, which are very well suited for computing these neural network architectures, or at least for fitting the model parameters. So combining all of that actually gave rise to what we call now these deep neural networks. So that just means that they have become complex enough, and we have found learning algorithms that can deal with this complexity, such that they now have shown to be much better than traditional machine learning algorithms on a wide range of tasks. Okay, and so that combined with the fact that they also allow end-to-end learning, and I will come back to that in a few slides, has made these deep neural networks much more powerful than what traditional machine learning algorithms can do. And so the ones that we have seen so far are referred to as the traditional machine learning algorithms. And so the problem that we observe in many tasks here is that if we here have increasing number of data, so this is actually a bigger and bigger data set for training, okay, and this is the performance, so better performance goes up here, okay. So what we see for traditional machine learning algorithms, they can do very well already with small data sets. For instance, support vector machine is designed using this large margin to deal with small data sets and potentially with many features. Now, what we see is that after a while, the performance starts plateauing, right? So we can give it more data, feed it more data, but it's not able to learn more complex relationships, right? Find more complex patterns in the data, so it plateaus off, okay? And what we find with these neural networks is that the more complex we make them, so the more model parameters we allow and the more data we have, the better they become, right? So they keep, it's actually kind of misleading, because we observe that they actually keep becoming better the more data we give them. And this is of course important, because here you can give it as much data as it's not going to improve anymore. While here you have these algorithms that keep improving once you give them more and more data, right? And since we're living in this big data accumulation period, this is very crucial, and this is why these neural networks have taken over traditional machine learning algorithms, especially in the case where there's lots of data. And these days on the internet, we have a lot of images, we have a lot of text. And so that's the kind of data that is actually advancing the field of machine learning these days. So the first deep learning architecture we will take a look at is the convolutional neural network. So it has convolutional layers. And the idea is to have a practical way of taking invariances into account. And so try to explain what I mean by that. So convolutional neural networks have shown great promise in image classification, understanding of images, image recognition. Okay, so in this case, so we see this image here of these nice three little dogs, and so suppose we have some, we want to build some classification model, a neural network that is able to look at an image and say whether there's a dog in there, yes or no. Okay, so in this case, the label would be yes, it's definitely a dog in there. Now, of course, if we look at the image, image consists of a number of pixels, right? So each pixel will have a value. In case of a color image, there will be 3 values, one for red, one for green, one for blue. If you have a grayscale image, this will be 1 value. So this would be what a computer sees of a grayscale image, right? And so the question asked to this model is, when you see something like this, can you tell me whether there's a dog in there, yes or no? Okay, so that's already much less trivial than what we have here. Okay, and so the invariances that I'm talking about, so let's just say that here we would try to fit a model where each pixel is a feature. Right, so we have this feature, this feature, this feature, and the value is, of course, the value of the grayscale for that feature. Okay, so the problem, of course, here is that, okay, we can have, we see these dogs here, but this dog could be somewhere over here. So if you're looking at faces, the faces could actually be everywhere. This dog could be looking up, for instance. There could be a different scale, there could be a small dog in here, there could be only part of a dog visual, and then also we want to say yes to the fact that there is indeed a dog in that picture. So that's the sort of invariances that I'm talking about. The objects that we're trying to recognize here, they can be distributed anywhere here in the picture, and they can have different scales and things like that, right? And so if we use features like this is going to be very hard, because just a small shift in the face, so moving the face to the left to the right, will dramatically change the values of these features. So you're going to need a whole lot of data to be able to learn something useful from features like this. Okay, and so what people do in image recognition, image classification, is they design their own features, right? And so these features would be something like, is there somewhere in this picture something that looks like a circle, right? And is there something that looks like a triangle? Now, making it very easy, the actual features are much more complicated, right? But that's basically the idea. And then based on all of those features, you would be able to classify whether there's a dog in there, yes or no. And since the features look at certain patterns anywhere in the image, you kind of modeling the invariances of the objects that you're trying to classify. Okay. So these features that I'm talking about, they are actually known as convolutional filters. Okay, so filters, and here we see such a filter. And don't worry, I will explain this in more detail in the next slides, but this is the main idea. So you would have a filter here, which in this case consists of 9 values, sorry. Okay, and so you would slide that filter over your image, so going like this and then going like this, zigzag over the image, so that the whole image is covered. And at each position, you're going to make a computation, yes, a convolution. Okay, so that's defined by what we have here, and I will come back to that in the next slide. So given this filter here, we're going to compute one particular value from this slice of the image, right? And so in this case, this would be -8. Okay, and then we just move this filter, right, one step. So it goes one step in that direction, and then we can have another value computed, right? And so we would reduce these values here to a new set of values here, which are obtained by looking through this particular filter here, okay? And so let's consider this slightly more complicated filter. So the idea is exactly the same. So this will be the filter, right? And so what you can see here is that this filter is actually recognizing a certain shape, right? So that's sort of this shape that this filter is looking for. So if we scan the whole image with this filter, what this will produce is an activation. So it will produce some output indicating that at that position in the image, we find something that looks very similar to this shape, okay? And so if we take the image here of a mouse, right, and so let's say we have this filter here, okay, and at some point we're scanning this mouse image and we say we get to this point here, then you can see that at this point here there is something that looks very much like what this filter is looking for, right? And so if we then do the convolution, so we multiply the image that we see with the filter, or the part of the image with the filter, we should get a high value, indicating that at that point we see something that looks very similar to this filter, okay? And so, of course, if we take the same filter when we look at some place in the image where there is no such thing, then if we do the convolution here, we should see very small value, indicating that there is, at that position, we don't see this particular pattern. And so the nice thing about these convolutional neural networks, and that's what's so new about them, is that we don't have to specify what the filters are in advance. So up to like 15 years ago, this is what people were doing. As lots of research went to finding better filters for specific situations. And then all of a sudden someone came up with this idea of learning the actual filters in a neural network architecture. So the filters would be model parameters on their own. They are somewhat special model parameters. We call them shared model parameters. I'm not going to go into detail into that. But the important thing to remember is that these filters I then just showed you that actually learn to recognize certain patterns in the image are learned from the data by the neural network itself. So they are not fed in by the user. And this, of course, makes a really big difference. And so this is a typical architecture of such a convolutional neural network. So what happens is that you have your input image, right? And then you have a bunch of filters, which we call here feature maps. So each of these squares here is actually looking for one particular filter. So it's actually trying to recognize one particular particular pattern in the image, and it tries to find out where in the image it finds these patterns, right? And so each feature map that we have is looking for a different pattern, and the pattern that it's looking at is, again, like I said, it's learned from the data. So it's actually learning which patterns to look at to actually, in the end, get a good performance on the actual task it's solving, right? And so you can have this also very deep. So you can have a feature map, right, looking at a certain specific pattern in the image, but you can have another layer on that, another convolution, which looks for pattern in these feature maps. So that would result in more complex filters, and I will show you an example of that in the next slide, right? And so that's exactly the same process, it's doing convolution on what has been convoluted, right? And then you can repeat that, and by that you will see that you get more and more complex filters trying to recognize more and more complex patterns. Another thing you can see in between is that we have something what is known as pooling or subsampling in between, right? And that kind of makes these feature maps smaller and smaller and smaller. And the idea would be that at the end we would have features that sound something like, I looking for something that looks like a nose somewhere in the middle of the image. So that's the level that we obtain here. Okay, and we can achieve that, like I said, by pooling. And so a very simple pooling strategy would be max pooling. That's what I'm showing you here. And so basically what that is doing is trying to put some invariance in the actual location of the patterns that you're looking for, right? So let's say that we have one filter. So this is the result of one filter scanning the image. So the filter is recognizing a certain pattern, and the filter is saying, okay, at this point in the image, I see something that might look like it, but it's not really close, right? And here is something that totally doesn't look like this pattern. Here's something that looks a little bit, this is even more. And then here it says, okay, here I can clearly see this pattern at this position here in the image, right? And so that's what the numbers represent. And so what we do is, in max pooling, is we reduce this feature map to a smaller feature map, right? And we do that very simply by just dividing this into pieces, right? Okay, and then for each piece here, like this part here, I just take the maximum value, right? So that would be 6. That's 6 here. I do the same thing here. The maximum value is 8, and here the maximum value is 3, and here it is 4, right? So what we learned here, or what we have now here, is something that says like, okay, I do see this particular pattern somewhere in the left top of the image, so somewhere here, right? Where it is not that relevant anymore because we only have this 6 here, but somewhere here we do see this pattern, right? And here, somewhere here, it's even closer to the pattern that we're looking for, right? And here, yeah, well, maybe a little bit, but not that much, right? So that's what the pooling is doing, okay? And so that, as you can see, that brings some invariance into the learning process. The model will be able to learn something like, I want to see this particular pattern somewhere there in the image, right? Not specifically at that location, but somewhere in the top left or something like that, okay? And so again, it is very important to understand that these filters are actually learned from the data itself. So you can imagine that there's quite a few hyperparameters on these models as well, being how many layers do we need, how many feature maps will we allow, what is the learning rate going to be, how will we do the regularization once we have a lot of layers in our model. So there's a lot of complicated questions that need to be addressed there, but once you have it, these models can be very, very powerful. And so, if you look at, let's look at the situation where we're building a model that tries to recognize cars, right? So let's say it wants to classify the cars by the factory they came from, or the brand, so something like that, right? And so it needs to find some representation of a car in an image, right? And so if you would fit such a convolutional neural network as I just described, then you could feed it many pictures of cars, annotated pictures of cars. What you would see is that in the first convolutional layer, so the first filters that are learned typically look something like this, right? So these are filters, low-level filters that look for empty spaces, black spaces, horizontal lines, vertical lines, a bit like these simple filters that I just shown you for the blurring and then these kind of things, right? And so that would be the first level. But as I showed you, convolutional neural networks will have different layers where each layer looks at the results of the filters of the previous layer. So this first layer would detect all of these, all of the regions in the picture where we see horizontal lines and vertical lines, okay? So if you go one level higher or several levels higher, you can see that the filters that are being produced are actually much more complicated because they are produced from the previous filters that are learned, and so you get more complicated and more complicated. And so in the case of this car neural network, you can see that somewhere in the middle of the neural network we have these neurons, you have these nodes, these layers that are trying to detect things that look like parts of cars. So you can see wheels here. You can also see other parts of a car. So it's higher level than the previous filters, but still not a car, of course. And so if you go way up in the more complex filters, you can see that it's actually learning filters that look very much like a car. So these are very general cars images that fit many cars pictures. Okay, so important lesson is that the deep learning in this case comes from the fact that you're actually learning representations in each level. So the first level is very low level filters, very abstract filters, like I've shown you here. And then when we go up and up and up, we get more and more complicated filters, which again, very important, are all learned from the data. And so we have other examples. So we have face recognition. This was the car one. We have elephant classification. This is for shares. So you can see that typically they will all end up with very much the same low level filters, but once of course they get more specialized, you can see the filters are more specialized towards certain objects like elephants or faces or chairs. A famous dataset in machine learning is the ImageNet dataset. So this is actually a very big effort which has been going on for years now to make a very big quality dataset with annotated images. So there's a lot of time spent on annotating these images and collecting these images. So currently this database, this dataset consists of more than 14 million annotated images. Right? So for each of them, we know what's in there. Okay, there's about 21,800 subcategories in there, and we have about 27 high-level categories. So this is what we call a very big data set for machine learning, and this data set has actually kicked off the deep learning revolution that we see today. And so I can show that here. So what we see, so what they do for the contents is that each year new images are collected and annotated, and the annotations and images are kept secret until one day in the year. So when the ImageNet competition starts, in that case the images are released but blind, so no annotations, and of course the contesters have to build models from the already the exit from previous year's annotations to do as good as possible on this year's annotations, and then at the end you get scored for those predictions you make, right? And so what you can see here is in terms of years, so the performance of the best model each year, okay? And so this is an error rate, right? So it's a specific image recognition task here. And so you can see that up to 2011, we had classical machine learning approaches where we were very happy to achieve like error rates of 26%. And then came Le Chun with his AlexNet. So this would be the first or one of the first published convolutional neural networks. Not too deep, 8 layers, but deep enough to show a very significant boost in performance compared to this. So this is where the community actually woke up and said, okay, we have something here, let's jump on this and see how far we can push this. And so you can see that every year this is pushed much further, right? So we estimate human error to be somewhere around this 5%. And so you can see that by having this more complex neural network, so this is Microsoft and Google and other big players that are doing this, because you need serious resources to be able to do this. You can see that you can get very high performant image classification models, so better than human error. So that also means that computers are, for instance, much better at recognizing faces than we are. So this is the reality that we live in today. And so, of course, it's not always that trivial. Computers do make mistakes, and humans do so as well. So you can see here in these images, it's not always that easy to find the correct classification. And finally, of course, since we're reaching these high levels of recognition, we're starting to find applications of these models, especially in face recognition, where it is used maybe as a tool for surveillance, but I mean, considering the social tracking that we need to do these days to get rid of this nasty virus that we're dealing with today, they might end up to be very useful tools, right? So you can see that you can really quickly scan a large number of people and track them. Yes. So another nice example here, which I want to mention, is this actually woke up people in biomedical sciences, medical people. So this was published in Nature not so long ago, where the researchers actually just said, well, we see this very good performance of this convolutional neural network for face recognition and all kinds of other tasks. How well will it do on this melanoma problem that I introduced in the first lecture, right? So we have these skin lesions annotated as malignant or benign. In this case, actually, they have annotated them by many more classes, but some of them are malignant, some of them will be benign. Okay, so they had quite a big collection of images. So these images annotated by dermatologists, some of them actually experimentally verified, most of them actually, but not all of them. Okay, and so what they did is, well, they showed, okay, we can have this deep convolutional neural network with a lot of layers in there and a lot of pooling, right? And in the end, we will have a model that can actually look at an image, right? So we don't need to compute any features anymore. We just feed it to the convolutional neural network and it will learn its filters from its own, okay? And then in the end, we will have a classification. And so what they show is that if you take several test sets, so we have different tasks here, so I can see the test set. So these test sets were given also to a number of specialists, the dermatologists. So in this case, we have 25, 22, and 21, okay? And so what you can see here is the ROC curve, right? So that's what we have here in blue, the ROC curve for the convolutional neural network, right? So that's the performance of the convolutional neural network. And in red, you see the performance of each of the dermatologists. And in green, we have the average dermatologist. And so what you can see clearly here is that the convolutional neural network performs at least as good as the expert dermatologist. And I would actually argue most cases they perform even better. Now, what's special about this algorithm, few people know this, is that actually they didn't train their algorithm on these 127,000. I mean, not fully, right? So what they did is they just went to the Google TensorFlow website. So this would be Google's implementation of neural networks. So you can actually download from their website trained neural network. So this actually network here is trained on these 14 million images from ImageNet, right? And so what they did is they just download this network, which means that you downloaded the fitted model parameters, right? And then they cut off a little part here, which is specialized into recognizing horses or these things. So you kind of use the low-level representations learned on the ImageNet, and then they fine-tuned it. So they actually kept training it from the point where it stopped training in the ImageNet, kept training it on these images, so that we now have a deep convolutional neural network that knows about images because it was trained on ImageNet. It knows about shadows and invariances and textures. And then it is actually asked to fine-tune itself to use that knowledge, that information, to focus on these skin lesions, right? So find new filters, additional filters that help you trying to make a classification for these skin lesions. Okay. So this is a process called transfer learning, where you don't have to start from scratch all the time. You can start from a network that knows about something. So in this case, knows about images, but you can also have networks trained on a large amount of text, for instance, on Wikipedia or something like that. And so that would be networks that know something about words and sequence of words in sentences. And then you can fine tune those models also towards more specific situations like medical journal papers or something like that. So another very famous competition in machine learning, we do like competitions in machine learning. So this is the CASP competition. So CASP, Critical Assessment of Techniques for Protein Structure Prediction. So the idea would be to get the primary protein sequence and try to predict the tertiary, and so the fold of the protein. So in this case, you can see the ground truth in green, and you can see the predictions of one of the best models these days in blue. Right? So you can see that here. And so just as with ImageNet, what's happened here is that each year new annotations are performed, so experimentally verified. They are kept secret, and again on one day the primary sequences, the protein sequences, are made available as a blind test set, and you are of course evaluated on how well you are able to predict the actual fold of that sequence. Okay, and so every year, like I said, we have this, or there is this competition, right? And so if you look at the competitions over the years, right? Well, if you look at this would be the group that has been winning this competition for many years. So this was the best performing model until we have this convolutional neural network architecture. So this is a very new approach to actually formulate this as a convolutional issue, so to learn convolutional filters to actually solve this folding problem. And so what they show is by having these deep convolutional neural networks for this, you can get a very, very significant boost in performance. So the folds are much, much better than what we have seen in previous years. So this again was very remarkable. It's the same as this AlexNet that showed this big reduction in our ability, or a big improvement in our ability to recognize objects in images. And so here we see this big improvement in predicting the fold of primary protein sequences. And so the second deep learning architecture that's very popular these days is what we call recurrent neural networks, recurrent layers. You know? And so recurrent neural network actually designed for data that's sequential in nature. So sequential data typically hard to represent by feature vectors. Feature vectors are fixed length, and in this case we have sequences that can be that are variable in length. And so this architecture, this deep neural network architecture, is designed to deal efficiently with these sequence datasets. So sequence datasets, natural language processing, of course. We have sentences, and we want to classify them, for instance, by sentiment. So is this what is the sentiment of this sentence? Is it positive? Is it negative? Paragraphs, which we might want to summarize or something like that. Of course, complete documents. We of course have a lot of biological sequences, right? We have the DNA sequences, RNA sequences, protein sequences. So there's a lot of sequence data that we have in biomedical research. Of course, videos is also a very typical example of sequence data. Okay, and so the difference with a normal neural network architecture is that you have some sort of a feedback loop here. So this would be a representation. This is what's typically used to talk about recurrent neural networks, where you would have the input here. So this would be your feature or features, okay? And so here you would have your hidden layers, so your deep neural network layers, and then you would have your output here, right? So the actual prediction that is computed. And so what you can see is that, of course, as we have in normal neural networks, we have a connection between the input features and the layers, the activation layers here, the neural network layers, which eventually will output one particular classification. But here we have another feedback loop. So each time you feed this network with features, right, it will also be, we will also feed it with the previous state of the network. Right. So at each point it gets as input the new state, the new set of features, and the previous states, right? And so what that means, let's just say, for instance, that we have a sentence, okay? So the sky is blue. Let's say the sky is blue, and so we want to run a recurrent neural network on that and say at the end whether the sky is blue, whether that is a positive sentiment or a negative sentiment. Let's just say that's a positive sentiment of the sky is blue, right? And so what happens is that in this case you would have a feature representation for D. So the first word in the sentence, D, and this can be a back of word representation, right? So where you have one feature for each word in the English vocabulary. Let's say typically that's around 9 to 10,000 words, and so it would have a value 1 for the word T, and it would have a value 0 for all the other words, right? So that would be a feature vector representation of the word T that we have, so D, right? From this sky is blue. So we would feed that vector here, and here we don't have an initial input, so that's some kind of typically set to 0, okay? Would feed that, and so that would produce some output, and sometimes we need this, sometimes we don't. In this case, we don't need this output, but it would also transfer the state that it is in here, so the computation that it made, to the next step, and the next step would be the next word. So we have the sky is blue, then the next word would be sky. Right? So we feed in the word sky here, and so what it gets is the current state, the sky, where that's sky, but it also gets some information about the previous state. So it also has some information about the fact that there is D preceding sky. Right? And so this sky is, so here we would have is, we would put is in here, the feature vector representation of is, and it would be fed also with the previous state of the model, and the previous state of the model is of course also dependent on this state, right, on all the other previous states. So by doing this, you sort of keep a memory at each point or at each state you enter. So here at the word this guy, at the word is, right, it has some memory of the previous words, so it's keeping that memory into these arrows here, and so that's why it's called a recurrent neural network, because it has some memory state in there that remembers, in this case, which word it has seen before it saw this word, right? And so that makes it a recurrent neural network. And we call this deep neural networks because you can have a lot of these connections here, so sentences can be very long. We use these also for protein sequences where we have feature vectors for amino acids, so we would feed in one amino acid at a time, and at each point we would reach some amino acid in the protein, and we would also have access to information about all the other amino acids that we have traveled over in the protein. Okay, so that's in a very small nutshell explained how recurrent neural networks are different from normal neural networks. So here is an example of a previous Kaggle competition where the goal was to take some video, right? So this is actually a sequence of images, right, which we feed in there one by one. And so at the end, the prediction would be the amount of blood that has been ejected, so the ejection fraction of the heart here, as you can see here. So that would be the prediction. And of course, as I told you, we can also have these models run over protein sequences, so looking at them, for instance, amino acid by amino acid, and then at the end the prediction could be something like what is the stability of this protein sequence, or what is the function, or where is it localized in the tissue, in the cell, right? So all of those things. So you can see that these recurrent neural networks are actually a very natural match to biological sequences, for instance. Of course, these are also very popular for automatic translation, so this is actually a task that is considered to be solved. So you just need some data, and you can have a model learn from that data how to translate that text into any other languages. Okay. Another nice example here, sorry. These days a lot of fuss in automatic driving systems, so actually cars should become robots that drive us from A to B. And of course you can see here also that in this case this is also a natural match with this kind of sequence data. And so you can see also here, and that's maybe important to mention, is that in the previous task we were actually scanning the protein or the video, and only at the end we would have a classification. Right. So only at the end it would say what the ejection fraction is, or whether this is a stable protein, yes or no. But neural networks come in very different architecture. So in this case, you would actually feed the image one frame at a time. But every time you actually feed it, you also want some output. So in this case, it would be like, is there a car in there, and where would that car be? So the output would be the position of the blue box here. Right? And so each time you feed an image, you get a different output. Right? I get a different output, but each output, so each time you feed an image, it still remembers the previous state. So it still remembers where the car was in these previous images, right? And so that's how it is actually able to anticipate, to learn anticipation in these networks. So, and of course, similarly, we can also look at, for instance, secondary structure prediction. So we have protein sequence here, primary protein sequence. And so we scan this sequence amino acid by amino acid. And at each position, we also want a prediction. Right? So not just at the end, but we also want a prediction at each position, indicating, for instance, whether that is part of a beta turn or a gamma turn. And so in the end, when we scan the whole protein sequences, we will have predictions for the secondary structure as well. So, and it becomes even more powerful once you start combining these architectures. So, for instance, we can combine convolutional and recurrent layers in deep neural networks. So, for instance, what you see here is the task of having as input an image. Right, so that would be the convolutional layer, and the output would be a sequence. So in this case, a sentence explaining what's actually happening in the image, right? And so you can fit these models and they can become really accurate. So these are predictions produced by these models. You can see here it's quite accurate. It's not always as accurate. So we have 3 dogs here and only recognizes 2 dogs in the grass. But here, for instance, you can see that it recognizes that 2 hockey players are fighting over the puck, which is true apparently, but you don't even see the puck, right? So it really is able to generalize these images very well. And of course, in order to do this, you need millions and millions of these annotated images, right? And so here's another example where it is attacked as a baseball player is throwing a ball in a game, while indeed you can hardly see the ball, but it just recognizes this from the scene of what is actually going on in the image, right? And so you can do that the other way around. So this is very recent research. So the goal here is to take a sentence as input, so that would be the sequence taken care of by a recurrent neural network, and the output would be an image, right, which should reflect what's in the sentence. So the bird is short and stubby with yellow on its body, so that's what you get. And so different models will indeed produce different images, but as you can see, the images are pretty accurate if you look at the actual question that is being asked here. So finally, I want to briefly talk about another area in machine learning or artificial intelligence in general, which has shown great advances over the last year, which is known as reinforcement learning, or in this case, deep reinforcement learning. And so the idea is that you have something called the environment, right? So let's say we're trying to learn how to play chess. So this would be a typical example where reinforcement learning comes into play. Okay, so we want to learn how to play chess. So we will have an environment, which would be the board itself, right, with a certain state, so where the pieces are. So that would be the environment with a certain state. Okay, and we would have an agent, in this case, the agent playing the game. So in the case of chess, we actually have 2 agents, otherwise it would be a very boring game. So we have the agent and we have the environment. And so what happens is that you start off from some initial state, which in chess is very well defined. Okay, and then one agent makes an observation, so it sees the initial state, and then it will decide on an action it will take, right? So it will take one piece and move it. Okay, so that's the action. Okay, and so then we have we changed our environment, right? So we have moved the piece. So now we have another observation. Now in this case, it could already be a reward, and I will come back to that later. But it could be a reward. The agent has performed an action that resulted in a reward. Now in this case, you're not going to get any reward until you reach the end of the game, and the reward will be you win or you lose, right? Okay, and so this thing repeats itself, right? So the agent takes an action, the environment changes, other agent takes action, environment changes until one of the agents wins the game. Okay. And so now the issue is, or where machine learning comes into play, is that, of course, at each point the agent makes an observation for the environment and it wants to take a good action, right? Not just any random action. It wants to take action that eventually will result in a reward, right? So winning the game. So this is a very intuitive learning scheme here, right? It's based on taking actions and getting rewards for that, and making sure that the actions you take result in rewards. And so that's where the learning is. In the beginning, it's going to take actions close to random because it doesn't know anything about the game of chess, and some of these actions will result in losing, some of them will result in winning, and so whenever it results in winning, it knows that it has to update its brain here, right? So this could actually be a big table with all the possible states of the chessboard, and for each of those states it would have an action to take, right? But you can imagine that this table becomes huge, and that's just for the game of chess. It's not even a very complicated task that we're trying to tackle with deep reinforcement learning. So we can't store such a table, and so we need generalization. And so that's where machine learning comes into play. We need some model. In reinforcement learning, this is called a policy that takes some state as input, right, and decides on what is the best action to take next, right, in order to maximize the reward at the end. Okay, so that is the framework of deep reinforcement learning. And so just to show you the relevance of these models these days, so we have two very recent publications again that actually also reached the cover of the magazine. So we have 2016 Nature, 2017 Science, and these are actually all about how these deep reinforcement learning algorithms are able to learn to play complicated games. So we knew about chess, that wasn't that complicated, but recently they also tackled the game of Go, which is much more complicated. It has much more different states of the board, and where they show that they could also outperform the best human player in that field. So these things made the cover of these journals. Now what's important is that the way these things learn, so as I just mentioned, you start off from a very bad chess player who doesn't even know the rules of the game, but it just plays, and sometimes it will be rewarded, sometimes it will be punished. And so by having two of these agents play against each other, so you would have two computer systems play against each other, both of them would be completely stupid in the beginning, but they would learn from their rewards. They would say, okay, if I do this, then I seem to get a reward, so that seems to be a good thing. Next time I'm going to do this. And so you can have these two computers play millions and millions and millions of games these days. And so after all these millions of games, they will become very, very good at playing chess or playing Go or any other board game, which is that the science paper is actually about, is that they designed some sort of a general intelligence that is able to tackle different types of board games. And this is, of course, the ultimate game of artificial intelligence, to end up with some general artificial intelligence that is able to tackle all of our tasks. So this is from another paper in Nature. So here what the researchers have shown, that they can actually learn to play video games using this deep reinforcement learning framework. Learning how to play video games, so by a model that doesn't know anything about video games, it doesn't know how to play the game, all it sees are the pixels. So this would be a convolutional layer that just looks at the pixels in the image. So it doesn't know anything else about the game than just the pixel. So it's pretty much playing the game just like we would be playing the game, right? So it sees these things as input, and of course it's playing, and in the beginning it's a bit stupid, it will not play very well, but after a while it starts to notice that I get rewards for not losing that ball or something like that. And so if you have it play for millions and millions of games against each other, you will get very good players. So in this case, they trained these on more than 200 old Atari games, and they showed that their one deep reinforcement network was able to outperform humans on all of these Atari games. And so here you can see an example of such a training procedure. So again, this research made it to the cover of Nature not so long ago. I'll start this thing here. Okay. So now this is one of those games. So it's probably you know this game. It's called Breakout, right? So again, you don't want to lose the ball. And so you would like have this deep reinforcement learning try to learn what the game is all about. So in the beginning, it will not get very far because it doesn't have any clue what the game is about. But it soon learns that by keeping that ball in the air, it gets rewarded. So the rewards are actually very immediate in this case. And so it will learn which actions to take in order to maximize that reward. Right? And so as you can see here in the beginning, this is only a few training hours. So here we have 120 minutes of training. It starts playing quite well, as you can see. Right, so it has learned how to actually optimize these rewards that he gets for doing this, for taking all these actions. And so after even more training, and that's what you see for many of these games, that it actually, you could call it overfitting. It actually figured out how to beat this game. And in this case, so all it has to do is make a hole somewhere against the wall and then send that ball through that, and then there you go. And every time you do that, you get a lot of points. So here's another Nature paper about these findings. So in this case, they looked at, can we have agents play hide and seek games and see what kind of crazy solutions they come up with. And so if you go to the website that is accompanied by this paper, it's a very, very nice website showing you very nice examples of what these deep reinforcement learning algorithms can achieve. So I think one of the main applications of these deep reinforcement learning models in biomedical research or medical research in general will be robots, right? So not just robots to help disabled people walk again or something like that, but also maybe robots that actually perform complicated surgery and stuff like that. So it seems like that is the direction that we're going. And so what I want to show you here is how we get to such complicated robot systems. So here, what I'm showing you here is some research not that long ago where they use these deep reinforcement learning algorithms to make figures in this, so they have some physical constraints, make them learn how to walk, right? So you can see that here, it is trying to reach the end of the lane, and so every time it is able to do that, it will get rewarded for that. And if it fails, it will be punished, and so it will learn the actions. So the actions is how to actually move these things to walk, right? And so, as you can see, after a number of training time, you can see that these things actually learn to move very accurately, right? So here's another example, right? And so this is of course virtual. I mean, you can imagine that you can have these runs millions and millions of times, right? And so again, in the beginning, these creatures didn't walk at all. They weren't doing anything, but after a few hours of reinforcement learning, where they get rewarded for doing good stuff, you can see that they become quite performant. So in this case, you would have some deep reinforcement learning model that knows something about walking and balancing yourself and all of these things. Right. So the next thing you can do is we'll be singing when we win. I'm sorry about that. The next thing we can do is actually transfer or take that trained model that knows something about walking and putting it into something more complex, like you can see here. So this is actually a real life robot, which has this model inside that was trained on the virtual robots, so on millions and millions of episodes. So in this case, your time is much more limited. You can't do this for millions and millions of times. But since it has already a good notion about how to balance and all of these things, what's happening here is actually fine-tuning this model to real-world situations, right? And so the idea would be exactly the same. I mean, you would set them to reach a goal, like the end of the lane. If they do so, then they get rewarded. If they fail, they get punished for that. Like, so that's what's happening here. And so eventually you would end up with robots like this, and this is a company I really like. They're doing really great stuff. So you can imagine that there's quite a complicated model in there that actually decides on which action to take and each step in the environment, right? So this is pure reinforcement learning that looks at the environment and decides on which action to take, and it has learned that from, as I have shown you, from these virtual reinforcement learning training sessions, and then the fine-tuning afterwards in real situations. And so, yeah, I mean, it speaks for itself that when we can do stuff like that, it's not going to take much longer than to actually get more fine-graded robot activity. So here we have again a very recent publication in Nature about grasping. So that's not that easy, but if you eventually want to do surgery, being able to grasp something is probably going to be a good asset. And so what they're doing now is using these deep reinforcement learning algorithms to train robots to find certain objects and to put them into the right box, and also to be able to pick them up accurately. Right? So these things sound very trivial, but they're not. But the nice thing is that we now have a deep reinforcement learning framework, and from the moment we have collected enough data, enough training sessions, you will see these robots perform better and better and better.